So in the following example, we're given a function and it's piecewise defined. It's defined in 4 parts. And the question says, for what values is f of x continuous? So if we look at it, I'm looking at this and I see, well, there is a 0 and there's 1 and there's 2. Okay, so 0, 1, and 2 are the numbers, of course, that we are interested in. All right, so what we're going to do is we're going to evaluate this function by taking a look at these sets of numbers. So the requirements for continuity, of course, are that the function is defined, the limit as x approaches a of g of x exists, and that whatever g of a was in step 1 equals the limit that you got in step 2. So I'm going to run through this and I'm going to look first. I'm going to check, is g of a defined? We could check that for 0, 1, and 2. So I'm going to write here defined. Okay, and I'm going to put x equals 0, x equals 1, and x equals 2. And if you look at it, it is defined because if you look right here, and let me try to switch color for you. If you look right here, it's defined there because you have a less than or equal to. All right, so it is defined there at 0. So here it's defined. Now let's check 1. Well, if I look at 1, I see it's less than or equal to right there. So it is defined at 1. So that's good. And now we check, is it defined at 2? Well, if you look here, this one right here, let's see if we can get it, and this one right here are a less than and a greater than, so it's actually not defined at either of those two. So 2 is out of the question. All right, so we can eliminate 2 as an option. All right, now what we're going to do is we're going to check what f of 0 is, what f of 1 is, because we don't need to worry about 2. So let's see f of 0. All right, we plug in 0, and the only one we can plug into is this right here, x squared, because that's the one that will take it. Okay, because that's where it's defined. All right, so then that's going to be 0 squared, and that's just 0. And then we can check f of 1. And to check f of 1, we would plug it in right here because that's where that is defined. So we're going to check right there, f of 1. All right, and so we say 2 minus 1 is just 1. So there we have that. Now what we do is we check the left and the right limit for 0, and then we'll check the left and the right limit for 1. All right, so let's say the limit as x approaches 0 from the left of f of x, well, we're going to take that to be sine of 0 because that's to the left of 0, and the sine of 0 from the unit circle is just 0. Then we check the limit as x approaches 0 from the right of f of x, and that is this 0 squared, okay, which is the second function there, so that's 0. So the limit in general as x approaches 0 of f of x happens to be 0. So this right here matches that right there. Well, it's actually this, I'm sorry. It actually matches this. Okay, so this is continuous. All right, and now we're going to check this one, the second part of this at 1. The limit as x approaches 1 from the left of f of x, and so that is going to be this 2 minus x function right there. All right, so we're going to say 2 minus 1, and that's going to be, let's see, actually no, that's not the left hand side, sorry. Let me erase that. The left hand side is going to be this function right here. This is the left of 1, so 1 squared. So 1 square. I was looking at that and it didn't seem right, so that's 1. The limit as x approaches 1 now from the right of f of x. Okay, this one right here is to the right of f of x. All right, so now we plug that in, 2 minus 1, and we get 1. So the limit in general, as x approaches 1, of f of x happens to be 1, since the left and the right hand side agree. And if we look, these two are equal, so this function is also continuous as well. All right, at 1. So for what values is f of x continuous? Well, it's at 0 and at 1, but look at all the work that was required in order to prove this. So again, the main point here is that you need to know this, the continuity.